Okay, so we're gonna talk about a number of things involving thermodynamics. We're gonna start by talking about work, and then we'll move on to the first law of thermodynamics, enthalpy, and how we use enthalpy to figure out the amount of heat arising from a reaction or being taken away by a reaction. So let's first focus on work. All right, there's two terms that I need to define for you. The first one is the system. And the system from the point of view of chemistry is technically any reaction that you're carrying out. Any reaction or any substance that you're looking at, any chemical substance, is what we do refer to as the system. And the surroundings is simply put anything else other than the reaction that you're studying. Now work, from the point of view of gases specifically, can be derived by the product of pressure and volume, specifically the change in volume. And if you think of your vessel right here on the left side, in this container that has a piston, a movable piston, if you decrease the volume of the flask such that you compress the gas via means of some type of potential energy, what you're basically doing is performing work on the system itself, because the system doesn't necessarily want to be compressed. Like if you have a gas at a regular volume, as shown here on the graph, spontaneously this will not change its volume to be smaller, specifically if you're dealing with gases. Gases try to expand. So this is not something that will happen on its own. So you actually have to do work on the system to allow this type of compression to happen. And what happens is that the work, as you can see, is going to end up being a positive work because you're doing work on the system. On the other hand, if you take the original gas and the gas expands, the gas will start pushing on the piston, thus increasing the volume. And now the system is what's doing work on the surroundings. So mathematically speaking, we say that, okay, the system now is losing amount of energy because it has to do work on the surroundings. So we'll have a negative term or negative sign associated with the calculations. All right, so this is kind of the idea of systems and surroundings, and it's a very rudimentary view of system and surroundings. If you guys ever take physics, you'll get into much more detailed descriptions of what a system and what the surroundings are, and being able to make that connection is very crucial to get the right answers when doing calculations of work and heat and internal energies. We'll see in a little bit. But for chemistry, it's actually rather simplistic. The system is just the reaction or the chemical in question. All right, now, as I was implying, technically speaking, we're going to be looking at the change in work done by the gas. Either you have the gas doing work on the surroundings upon expansion, or you have the surroundings doing work on the gas by contraction or compression. And what that also means is that the change in work will be attributed to the change in volume. And because the final volume tends to be less when the work is positive, that means that we need to put a negative in front of the pressure times the change in volume, because the change in volume, having a volume that is less as the final volume, when they give you a negative value for the change in volume. And another thing to point out before I get any further, the terms that you see here, D, this is not density, this stands for change. Technically it should be a delta, but it was a little inconvenient to write delta in the PowerPoint, so I just left it as little d. But this is delta W and delta V, which stands for change in work and change in volume. All right, so here we go. We're kind of stating that concretely now in the PowerPoint. So these changes in volume are going to affect things quite a bit. All right, now, there's two situations that you have to consider when dealing with work. In one instance, you may be dealing with work that is conducted under constant pressure. But in other instances, you might be carrying out work that is done under variable pressure. And in the problems that I will have you do, if I personally don't mention anything about the pressure, I automatically assume that the pressure is variable. I will have to go to my way to tell you the pressure is equal to this value and it's constant for you to assume that the pressure is constant. Okay, so otherwise, assuming it's variable. All right, now the reason why you have to look at it in these two terms is because the equations themselves change a little bit. They both derive from the idea that the W equals negative P times dV. But at variable pressure, as the name implies, the pressure is going to be changing. Uh, and one way to approximate that in terms of volume is to rewrite pressure using the ideal gas law. So PV equals nRT. And if you solve for P, you're going to find out that nRT divided by V is nothing more than the pressure itself. And what you're doing is restating pressure as a function of volume. Okay, and that's kind of like the idea of having variable pressure. All right, now I'm going to kind of skip a step right here because it does involve calculus. But technically speaking, these are what we call changes in variables that can be determined to a concrete final value by using calculus, specifically integrals. So if you were to take the integral of the change in work, you just get the work. And if you take the integral of the constant pressure times the change in volume, you just get the pressure multiplied by the change in volume. Okay, so it's the same thing. The trick is definitely much more impressive when looking at variable pressure, because when you apply calculus to this, you get something sort of similar but not exactly the same. You get that the work is equal to negative nRT multiplied by the natural log of the final volume divided by the initial volume. This you would only arrive at if you perform calculus. This is technically the integral of 1 over x dx, which is ln of x final over x initial. So this is directly from calculus, and I'm not going to have you do calculus here, so I'm just kind of giving you the equations for you to, do your thing. All right, so these are the two equations that you have to keep in mind when doing work. Depending upon whether the problem deals with constant pressure, you will be using this version of work. If the question implies or doesn't say anything about pressure at all, then you assume that it is variable, and as far as performing the calculation for work, you will concentrate on this equation. And I'm going to use these two equations in a little bit when we do a few examples. All right, now this is done at constant temperature, just to kind of keep that in mind. But let me show you one more thing in regards to work before we get into deeper territory here. The units. All right, so this is the thing. I'm saying that work is the product of pressure times volume. All right, so let's say that we have a pressure of 1 atmosphere and we have a volume of 1 liter. If we multiply those two together, pressure times the change in volume, we're going to get the work. All right, well, fantastic. But the only issue is that if we do that, we're going to end up with this funky unit. We're going to get 1 atmosphere times 1 liter equals 1 atmosphere liter, which is technically work. But these units are not traditional units that we want to be using with work, because after all, if you remember from the last lecture, energy, which can come in the form of heat or now, as you can see, in the form of work, is traditionally given in units of joules. So what we're going to do is carry out the calculation, the conversion, in fact, from atmosphere to liters. And it'll be a conversion that might be a good idea to keep in mind. It might simplify the process. So we have the 1 atmosphere liter. So what we want to do is change the atmosphere to units of pascals. Okay, and the reason why is because pascals, technically speaking, if you spell out what a pascal is simply kilograms divided by meters second square. And 1 atmosphere contains 101,325 pascals itself. So that cancels out the atmospheres. Okay, now what we're going to do is we're going to change the liters to mLs. And we know that since we have liters on top, we place them on the bottom. That's equivalent to 1,000 mLs. The liters cancel out. All right, now we're going to change the mLs to cubic centimeters. And for every 1 ml, there's 1 cubic centimeter. So that's perfect, not too bad. Finally, we're going to change the cubic centimeters to cubic meters. And in order to do that, we first use the conversion of 100 centimeters equating to a meter. That entire fraction needs to be cubed. Hopefully you guys remember this from our first lecture. So if you distribute the cube, you're going to get now 1 cubic meter being equal to 10 to the 6th cubic centimeters. Now this will allow the cubic centimeters to cancel out. And now you can perform the calculations. Now if you look carefully, you have cubic meters on top of this fraction. On the denominator of that fraction, you have meters. So that's partially going to cancel out to give you meters square. And the units you're going to end up with will be kilogram meter square over second square. And upon doing all these multiplications, what you ultimately end up doing is dividing the conversion of Pascal by 1,000. So you end up with 101.325 kilogram per meter square second square. Now the kilogram meter square second square, we stated this in the previous lecture, is the same thing as joule. Okay, so what this means is that your conversion from atmosphere liter is simply equal to 101.325 joules. And that's how you go back and forth in case you get into this funky territory when dealing with work. And just as a final example, if you look at the gas constant, 0.08206 atmosphere liter per mole Kelvin, we did the entire derivation like I showed right here on the previous lecture, actually probably lecture 9. But here now we can just use the conversion that we just derived. We know that atmosphere liter, well, 1 atmosphere liter equals to 101.325 joules. So the atmosphere liters will cancel out, and you're going to end up with 8.3145 joules per mole Kelvin. So that's your conversion pretty much. And as far as the gas constants go, just remember 8.3145 for joules, 0.08206 for atmospheres, atmosphere liters if we want to be technical. Alright, we're going to continue this lecture on the next video.